next example, I want to do a compound that looks like this, CHI3. Okay. First thing we want to do is count the total valence electrons. So I consult my periodic table looking at the columns and what the valence number of electrons should be based on certain columns. All right. So carbon is in group 4, so it should have 4 valence electrons. Plus hydrogen is in group 1, it should have 1 valence electron. And plus iodine is in group 17, so it should have 7 valence electrons. But there's 3 iodines, so that's going to be 7 times 3 valence electrons. All right, so this should give me a total of 26 valence electrons. Okay, so the next thing I want to do is connect all the atoms to the central atom with a single line. All right, so I'm going to probably put carbon in the middle here. Carbon is very frequently a central atom, and hydrogen can never be a central atom. And I also want to do kind of make these structures symmetrical, so I want to make them sort of spread out the different kinds of atoms all around the different sides of the central atom. And I couldn't really do that with 3 different iodines. So carbon is going to be our best central atom here. And I'll connect the hydrogen with a single line, and then the 3 iodines, kind of like that. All right. So it's sort of symmetrical, the best I can get anyway. And then I want to do step 3. For each line, which represents a bond or a shared pair of electrons, I want to subtract 2 electrons from the total valence number. So I just drew 4 bonds, or 4 lines. So I'm going to subtract 2 electrons for each line. So I'm going to do minus 8 electrons here, and I'm going to have 18 electrons remaining. Right? So with the electrons remaining, I want to give every atom an octet, but there's a big exception to this, except hydrogen. Right? Because if you remember, hydrogen only has 1 energy level, and it usually has 1 electron. That first energy level can hold 2 electrons. So if hydrogen has a bond going to it like that, it's like another atom is donating an electron or sharing an electron with it. But since hydrogen has only that 1 energy level, it's full when it has 2 electrons. So as soon as you draw a line going to hydrogen, it's full. It could never have dots around it like that. Okay? So you don't want to ever do that. Once you have a line going to hydrogen, that's all you can put on the hydrogen. All right, but I do want to do this step 4 with my 18 electrons remaining. I want to try and give every outer atom an octet except hydrogen. All right, so I'm going to put around the iodine, I'm going to put 6 electrons. Around this iodine, I'm going to put 6 electrons. And then around this iodine, I'm going to put 6 electrons. And that would use up, of these remaining ones, I just used 6 electrons on 3 different atoms. That was 18, and I have 0 electrons remaining. So that's good, because now I want to check my work, and I want to see, does my drawing show all the total valence electrons? In other words, does it show all 26 electrons? So let's count them. We've got 2 in this bond, plus 2 there, that's 4, plus 2 there, that's 6, plus 2 there, that's 8. And then let's count these lone electrons. We got 2, 4, 6, 8, 10, 12, 14, 16, 18. So I got 18 plus 8, that gives me 26, which matches my total valence electrons. So I can say yes to that first one. I did use all the electrons I was supposed to. And then the next thing I have to check is, does every atom except hydrogen have 8 electrons? So let's count them. This iodine here has 6 dots plus the bond, which is another 2, so that one has 8 electrons. This iodine has 6 lone electrons plus 2 from the bond, so that's 8. This iodine has 6 lone electrons plus 2 from the bond. That's 8. And then my carbon gets to count all those bonded ones. So it's got 4 bonds going to it, so it is surrounded by 8 electrons. And then look at the hydrogen. The hydrogen doesn't have any lone electrons, but it has 1 bond going to it, which means it has 2 electrons. So that's perfectly fine for hydrogen. Hydrogen can have 2 electrons, but no more. Hydrogen cannot have an octet, since it only has 1 energy level. It can only hold 2 electrons. So this is my final Lewis structure for CHI3. Let's do one more where we have to do a double or a triple bond. SiO2 for this example. Alright, silicon is in, first thing we want to do is count the total valence electrons. So silicon's in group 4, so it's got 4 valence. Oxygen is in group 16, so it has 6, but there's 2 oxygens here, so we got to multiply that by 2. So we get a total of 16 valence electrons. Okay. Now, we want to connect all the atoms to the central atom with a single line, and in this case I'm going to make silicon the central atom so that I can get a little symmetry, make it look a little uniform out here, and do that. Silicon in the middle. For each line, which represents a bond or a shared pair of electrons, I'm going to subtract 2 electrons. So I've got 2 lines, I'm going to subtract 4 electrons, which would give me 12 remaining. Right. Now with the electrons remaining, try to give every outer atom an octet. So let's put 6 on that outer atom and 6 on this outer atom. And so we used 12. We have 0 electrons left remaining. Then, so we've done that step. And let's check our work then. Let's do this. Does our drawing show all 16 valence electrons? Let's count them. There's 2 in that bond, plus 2 in that bond, that's 4, plus the lone electrons, 2, 4, 6, 8, 10, 12, for a total of 16, which matches our total valence electron there. So, yes, we have all the total valence electrons shown in our drawing diagram. Alright, the next thing we have to look at is, does every atom except hydrogen have 8 electrons around it? And I can look at this oxygen and say yes, because it has 6 valence electrons plus 2 in that bond. And then this oxygen has 6 lone electrons plus 2 in that bond for 8. But the problem is with the silicon. If you look at the silicon atom, it has 2 electrons there and 2 electrons there. So silicon is surrounded by 4 electrons, but not 8. So that is not good. So since that is not true, since every atom is not surrounded by 8 electrons, we have to do something else. We cannot just add electrons to this diagram. We can't just do that, because now instead of 16 valence electrons, we have 20 valence electrons. So we can't do that because we're trying to stay with this 16. All right, so we have to figure out something else. We have to work with the electrons we have. So what we have to do is take some electrons that were lone electrons to oxygen, and we have to move them into a shared position right here. Right? And then we have to take these lone electrons and move them into a shared position right there, for a total of 16 electrons still. And then our silicon is still surrounded by 8 electrons right there.